Okay, I think most people are here already. I will slowly get started, so if you missed the first part, you can just go back. I'm going to do two things today. I'm going to have a lecture on multiple testing and how to correct for it, and I will go over the solutions of the t-test exercises. I will post model solutions after this, but yeah, first let's just discuss the assignment, see if there were any trouble. So yeah, the first exercise, you just have to copy this data to R. So let me show you how I would do that. Also, so you can, see the regular workflow. So first thing I would always do is just create a new R Markdown file because it is way easier to keep track of what you've been doing. These don't really matter, but let's just do it anyway. Solutions. Yeah, and then you can delete everything that's not the preamble. Preamble is this little part at the top with the 3 dashes, and then you can insert a new chunk. There's different ways to do it. So you can do Control-Alt-I, it's easy, or you can use Insert and then choose R, or you can just type this. Okay, then I paste this. So yeah, for those who didn't saw, there's a copy button over here, so easy way to copy the entire chunk. Then when we run this, we have the 4 different vectors stored into our memory. So, okay, let's have a look. We have 2 different types of birds, and we're going to compare the length and the depth of their beaks. Well, there's different ways you could go about this, but you could, start by noting that, they probably vary to the same extent, right? There's no real reason why different species would have different variation in their beaks. Because if they did, they'd probably be different species. So this would be a good reason to use t-test with equal variance because it gives you slightly more power. And also, I think normality is a very reasonable assumption here because you can assume that most beak lengths are about the same and that deviations in either direction, so shorter and longer, are equally likely, and that further deviations are exceedingly rare. And that is essentially what the normal distribution says. So yeah, it's probably not exactly normally distributed, but approximately normal is a reasonable assumption. On purpose, in this exercise, there are too few observations to do any kind of meaningful analysis of whether this is approximately normal. You can't say whether something is approximately normal with 3 or even with 6 observations. So you have to think for yourself which makes more sense and then apply that one. So let's do that using t.test. And then let's start with the length. So I want to compare the length of one species to the length of the other species. Yeah, so this is one option. Another is to choose var.equal is true, which will give you the slightly more powerful version, which in this case I think makes sense to do that. But the other one is not wrong, it's just slightly less powerful. So if we run this, we get a p-value, and yeah, there is a significant difference in the length, and you can see that the second group, mean of y, is larger than the mean of x. Okay, so you can do the same for the depth, and you can use the same type of t-test for the depth, so I'm not going to show that now. So let's go to the next one. If you use a Wilcoxon test instead of a t-test, how does it affect your conclusion? Well, let's start by what do you think? Anyone have an idea? So now I use the t-test, which assumes that things are normally distributed. If I use a Wilcoxon test, which converts everything to ranks, how will that change the outcome of the test? Yeah?
When I did the test, I found that the p-value was
Equal to 1. Okay, let's see if that also happens for me. So let's do the same one, but now with a Wilcoxon test. And remember, the Wilcoxon test makes no distributional assumptions, so it doesn't have the var equal argument. So I'll just remove this last argument, like this. Okay, I get a p-value of 0.1. So yeah, that means that if there is no difference in the 2 groups, then there is a 10% chance that you would observe this large a difference. That is rather large, and it's larger than the commonly used 0.05. So this test is way less powerful than the t-test. And the reason for that is because when you convert things to ranks, you just have rank number 1, 2, and 3. So you're throwing away a lot of resolution in your data. Here we have very precise measurements, right? This is, I don't know how, but these are measurements in to the 100th of the millimeter. Oh, sorry, my screen is turning off. So yeah, it's always a less powerful test, except when there's very large deviations from normality. In that case, occasionally Wilcoxon test can be more powerful, but that's rare. So if you can assume normality or approximate normality, because a t-test is fairly robust against small deviations from normality, so it doesn't have to be exact, then you should use the t-test because it is way more powerful. Yeah, in this case, you know, we could just measure a couple other birds, no big deal. But you know, if we would do any kind of destructive sampling on the birds, or if there were any ethical concerns with tagging them and grabbing them, maybe they get scared, then you know, a t-test is not just more powerful, but it's a more ethical choice, because if it is more powerful, you need fewer samples. Yeah? Okay, then the third one, suppose you measure 3 juvenile G. fortis finches, tag them, and then measure them once again once they reach adulthood. What is the difference here? What do we want to do instead of the other one? Paired, exactly. Because these are the same individuals, right? We just measure them twice. And the reason the data are paired is because you can reasonably assume that a bird that already had a large beak when it was young almost certainly still has a large beak when it reaches adulthood. So these data are correlated. Yeah, so the only thing that differs is you choose the paired version of the test, and other than that it works the same. Okay, then we had the second one. This is much more akin to what you can expect on the exam, at least questions 1 to 5. The ones after that are purely for who had time left and has no real relations to the exam. It's more difficult. So if you were able to answer 1 to 5, then you have more than enough understood what I wanted to tell you about the t-test. Okay, so let's get started. First, we have the output of this t-test, and the question is, what kind of t-test is this? So let's start by, how can you tell? Does anyone have an idea how you can tell what kind of t-test this is? Yes?
Degrees of freedom if it's integer.
Exactly. We see a non-integer number of degrees of freedom. Also, a bit on the nose maybe, but we see t, and the t belongs to the t-test, so it's not a Wilcoxon test. So when there are non-integer degrees of freedom, that means that this was an unequal variance t-test. Now, we also see that there's 2 groups, so that means this is a 2-sample t-test, and we see a 95% confidence interval where 2 bounds are estimated, neither is infinite. So that means that this was a 2-sided, 2-sample, unequal variance t-test, yeah, or in other words, the default Welch t-test. Okay, and then you can use the output to determine the standard error. There's different ways you can do it, because there's redundancy in the information here to calculate this. For example, you could do it with the confidence interval, but a much easier way is to just use the t-value, because for difficult t-tests and for easy t-tests, it all works the same. It's always a difference in means divided by a standard error. The only thing that differs is how that standard error was calculated. So in this case, we can just calculate the difference in means, because we have both means over here. And then we can use the t-value and then flip it around, the formula, and then we know the standard error. Then we have number 3, and again the question is, what kind of t-test was used here? What's different about this one? Shall I make it bigger, or is this okay? Bigger? Yeah, okay, so what's different? This is number 3, in the output of number 3. Yes?
It's one-sided
How can you tell?
because of the infinite
Yeah,
confidence interval.
exactly. So this confidence interval says that the difference is at least minus 10, at least minus 0.1 millimeter, and it can be anything larger than that in the negative direction. Yeah, so it only estimated one bound. Okay, Julia asked, do you need to specify it being two-sided, or is that assumed to be the default when you say two-sample t-test? There's an easy way to find out. You just go to the website for it, because it's all open source, so you can find all of it. But now we're going to look at the documentation side, and then you can see what the defaults are. Yeah, so this is the same as if you would go to R and you do question mark t.test. Yeah, and it will bring you to the help page, but yeah, I don't have a lot of space there. So let's make this a bit bigger. What does it say? It says x, comma, y, alternative is c, two-sided, less greater. Okay, that doesn't really help. What does argument say? It says a character string specifying the alternative hypothesis must be one of two-sided, between brackets, default. Yeah, so it's a bit of a search, but that means that two-sided testing is the default for this t-test function. Okay, yeah, here you have to compare the p-value of the first and the second t-test. Yeah, so I will highlight the first one, that's this, and the second one, that's this. What do you notice about these two tests? Let's start by saying these were probably done on the same data, because the t-value is exactly the same, right? Degrees of freedom are also exactly the same. What is the difference in p-values? Yes?
The p-value for the two-sided test is 2 times the p-value for the one-sided test?
Yeah, exactly. So it's not more or less 2 times the other one. It is exactly 2 times the other one, because we're assessing only one of the two directions. So that costs half the probability mass of testing in both directions. So a one-sided test will always have your p-value for a symmetric distribution, and the t distribution is symmetric. Yeah? By the way, if you want to read about this, oh, it's not on this computer. How can I do that? Oh yeah, there we are. Yeah, so on the GitHub page, I linked to it several times. I can share the link later if anyone doesn't have it. You can find the book, you can download it if you want. And then in chapter 7, I talk about hypothesis testing in general, which is what we're talking about now. So let's go down there. Oh. I just quickly want to show what it looks like when something is one-sided or two-sided. There we are. Okay, so for a one-sided test, this is what the confidence intervals look like, right? You're basically saying it is at least this large, can be any other value, as long as it's larger than that, because we're only assessing one direction. So this is when you're when you're testing in one direction. This is when you're testing in the other direction. So that's what the confidence interval looks like. This is what how the p-values are calculated. Yeah, when you have a one-sided test, then you're only looking at one tail, because you're only interested in either a positive t-value or a negative t-value, but not both, because you specify direction. Okay, then we can continue. Oh, still this one. To number 5, which is the last one that I think you should understand to pass the course. What was the total sample size of the data used in the t-test below? Anyone know? Yeah, and why? Yeah, so again, this is a 2-sample t-test, because there are 2 group means. So that means we use 2 degrees of freedom. We have an integer degrees of freedom, namely 38. So that means that the sample size was 38 plus the number of things estimated. Well, we have 2 means estimated, so the sample size was 40. Yeah. So those are the things that I think you should know. These, I will post solutions, but they're just, you know, for people who are done quickly, and this level of questions you will not get on the exam. Are there any questions still about the assignment? Otherwise, I'll continue to the lecture. Okay, but before we start, I want to ask, question to you guys. Let's say 1 year from now, I'm going to ask you questions the same level as the exam. Who thinks that they have forgotten everything from this course? Okay, I see no hands, so that's good news. Who thinks that they have forgotten about half? Okay, okay, that's almost everyone. Who thinks they have forgotten more than half? Okay, no one, good, very good. Who thinks they've forgotten less than half? Okay, a couple of you, okay, you'll be fine. For those of you that think you're going to forget about half of this, that's fine, we will recapitulate this. But for your future, be it as a scientist or in any kind of business where you're ever going to use a test, this is the most important topic. If you want to use a significant test, you have to know what the multiple testing problem is, and you have to know a basic correction for it. So multiple testing basically means that you perform more than one significance test. So yeah, I've written down a couple of probabilities here. Of course, if you roll a fair six-sided die, there should be a 1 in 6 chance that it comes up with a 6, right? Because all of the faces of the die have the same chance of coming up if the die is if the die is fair. Sorry. But if you roll it twice, then you have two different chances of rolling a 6, right? So the chance of rolling 6 twice is 1 in 36, but the chance of rolling at least 1 6 is actually almost 30%, right? And if I roll the die 3 times, the chance of at least 1 times 6 is already bigger than 40%, etc. So this applies to significance testing. If you perform more than one significance test, then every one of them has its own chance of a false positive, and thereby the chance that at least one of your tests returns a false positive is much, much larger than the alpha value, the level of significance, that you agreed upon. Yeah, so let's say you work with a level 5%, then if you do 2 tests, it's already closer to 10%. If you do 3 tests, it's around 14%, but we're going to see the exact calculation in a bit. So the problem is that every test can get its own false positive, so you could even have multiple false positives. And thereby the chance of at least one false positive is much larger than is acceptable. There is a very simple correction, which is just to multiply all your p-values by the number of tests. That's called Bonferroni. And there is a much more powerful correction based on the false discovery rate, which I will discuss last. I just want to mention that there are other ways to deal with the multiple testing problem. I think the most successful of which is the local false discovery rate, but that requires you have at least basic understanding of Bayesian statistics, which is a bit more involved. So that's not part of this course. I just want to make you aware that there are more complicated ways to deal with this. Okay, so let's quickly one more time recap what a hypothesis test is and when we call something significant, because that is vital to understanding this problem. So the first thing you do, if this is a clinical trial, you actually have to register this, is to choose the acceptable chance of a false positive. So yeah, almost everyone works with 0.05. It's an arbitrary number, you can choose something else, but using 0.05, it's not wrong. It's fine as long as you state that before seeing any of your data. So in a clinical trial, you have to register this, and you cannot come back after getting some data and say, hey, we changed it to 0.1. That doesn't work. Then you come up with a null hypothesis, right? Which is some sort of statement that there is no effect or no difference, that nothing is going on. And you're going to collect evidence against that statement, because if you have enough evidence, you can reject the null hypothesis and conclude that, okay, apparently there is a difference, an effect, or whatever. Yeah? So then, for a t-test, you would calculate the difference in sample means. And yeah, you say, okay, this is how large the difference actually is. Is that significantly non-zero? Well, the way to do that is to compute a standard error of this difference, and then we divide the difference in means by the standard error, gives us a t-value. We calculate the surface area of that t-value onwards, and that gives us the probability of getting this large a difference. If the difference were 0, that's the p-value. If this p-value is lower than the value that we agreed upon, then we say, well, there is a less than 5% chance that this is a false positive. So we reject the null hypothesis in favor of the alternative that there must be a significant difference. So yeah, a low p-value just means that there's significant difference in the sample, right? It doesn't prove that there's a difference in the population. It just means that the chance of this being a false positive is less than the chance we agreed upon. But there's still always a chance that your one sample is significantly different, even though in the population the groups are actually the same. And the question is, how large is that chance? That is alpha. That is a chance that you agreed upon. It's not the p-value. The p-value is just a function of your sample, but alpha is the chance that whatever you are researching, if it is significant, that it would be a false positive. Now, the thing that we want to do in multiple testing correction is to make sure that even when we do more than one test, there is still a maximum chance of alpha of false positives. Okay, then finally let's quickly recap the correct definition of a p-value, which is the chance of observing a difference at least as large as the one you observed if in the population there was no difference, right? And you might think, okay, how is that possible? Very simple, it's a sample. Samples can always differ to some extent from the population, but you wouldn't expect them to be very different from the population. And the point where they are so different that it's lower than alpha, then we say it's significant. So what that means is, in any field of science where what we call an empirical field of science, so any field of science that bases its conclusions on evidence from observations, from experiments, and not from mathematical proof, is subject to chance, right? False positives, false negatives, they will occur. And there's nothing we can really do to prevent that. The only thing we can do is we can control these chances, we can limit them. And that's what this is all about. And of course, since the p-value just states what the chances of observing this extreme an effect, if there is no effect, then if you do, just like rolling the dice many times, if you do multiple tests, then every chance has its own chance of an extreme result. So across all those tests, the chance that at least one of them has an extreme p-value is much, much larger than alpha. Okay, to be precise, the chance of at least one false positive among k tests is equal to this. Yeah, 1 minus alpha to the power of k. So here, k is the number of tests, alpha is the agreed upon maximum chance of a false positive. So if you work with p-values lower than 0.05 as significant, then alpha is 0.05. So we can calculate from this what the actual chance of at least one false positive is. So if we just plug in the number, one test, then we see that indeed there's a 5% chance of false positive. But let's say that you're doing 5 tests, then the chance of false positive is actually already greater than 1 in 5. It's 22.6%. So that's all there is to it. You can change alpha, you can change k, you can see how it affects the chance of a false positive. But we're going to have to do something to make sure that it is no bigger than the alpha level that we want. Now, this can be done very easily. This is called the Bonferroni Correction, and it turns out that if you just multiply your p-values by the number of tests, then that guarantees that the family-wise error rate is at most alpha. So this is a very safe option. And it's the same as dividing your alpha level by the number of tests. So if you work with 0.05, but you're doing 5 significant tests, then you could work with alphas 0.01 instead, and you will have a maximum chance of 5% that among those tests there is one false positive. Yeah, so that's how you can correct for it. This is the correct way to do it. There's nothing wrong with this, but it's not very powerful. So that's why we're going to discuss another option. So the Bonferroni correction guarantees that the chance of false positive is at most alpha. From a standpoint of false positive, it's a safe option, but it's very strict because, let's say you're doing 100 tests, that means you're multiplying all your p-values by 100. If you do 1,000 tests, you're multiplying everything by 1,000. So that means that the extent to which something has to be significant is so much more once you do this correction than it used to be. And it's also a bit pessimistic. because this is the correct calculation for the chance of at least one false positive if all null hypotheses are true. So if you're doing 10 tests and all of those 10 tests are nonsense because they're in the population there is no difference, then the family-wise error rate is the chance of a false positive. But if you apply correction and there's still a significant result, then apparently there were real differences in the population. Not all null hypotheses were true, right? So what we're going to do is we're going to try a different correction that still, hopefully guarantees that the number of false positives stay low, but is also more friendly to the number of false negatives, so it preserves power. The way to do that, the easy way to do that is called the Benjamini-Hardberg procedure, which is a type of false discovery rate correction. It's also not a very complicated correction. The thing you do is you order all your p-values from most significant to least significant, so that means from low to high, and then you write down the rank, right? So the most significant one gets rank 1, second most significant one gets rank 2, and the last one gets rank k, right, for the number of tests. And then you correct the p-values by multiplying all of them by a fraction of k. So in the Bonferroni correction we would just multiply everything by k, but here we multiply by k and then divide by the rank. Yeah, so if you are the second p-value, then it's not calculated as p times k, but p times k divided by 2. And if you're the third one, it's p times k divided by 3, etc. That's the important part. Then there is a minor addition to it, because doing this, you're going to multiply every p-value by a smaller amount, so that might change the original order of the p-values, and we don't want that. And we restore the original order by saying that every p-value must be at least as low as the one next to it, because that preserves the original order that the most significant p-value is the most significant one, the second most significant p-value is still the second most significant one. Yeah? Okay, so what this does, it's a form of false discovery rate correction, and the logic behind it is that if many of the things that you're testing are actually significant, then apparently not all null hypothesis is false, and then you should apply a less severe correction than the Bonferroni correction. Well, how much less severe? It turns out you can just use a fraction calculated by the rank, as I just showed, and that turns out to be the right way to do it. So that's very convenient because it's very easy to do. And then the most significant p-value has rank 1, right? So it is still multiplied by k. So it is still in principle as strict as the Bonferroni correction, while allowing more significance after correction. Okay, in R, you don't have to do this by hand. You don't have to calculate the ranks and everything. It can be done very easily. So here we have a vector of p-values. This is the most significant one, and then we have 2 of these. If you would look at this nominally, so that means without correction, and your alpha level is 0.05, then you would say, oh, okay, all of these are significant, right? Because they're all less than 0.05. But actually, if you apply a Bonferroni correction, then, well, there's 3 tests, so we should multiply them by 3. And then these two, this one and this one, they'll be 0.06, so they're no longer significant, right? Well, what does FDR say? It says, okay, yeah, the first one, indeed, you should multiply by 3, but, I mean, this is still significant after multiple testing correction, so apparently there are real differences, and we shouldn't multiply by 3, but a little bit less than 3. And then the next one gets a lower p-value than you would for Bonferroni. So it is, it is a more powerful correction because it leaves more significance while still protecting against false discoveries. Okay, the big question is then, of course, why would you ever use Bonferroni? Because FDR still protects you against false positives and it is more powerful, so who cares about Bonferroni? The first thing is, of course, that Bonferroni is very easy to do. If you're reading a paper and they have 5 different results where they use a t-test or something, but they didn't apply multiple testing correction, then in your head you can already apply this correction. Just multiply it by 5, right? So it's very easy to do, it's correct, so that's one reason you would want to use it. Also, I don't think this is going to apply to any of your research, but if you are doing very large-scale research, then it can be useful that something is easy to compute for reasons of speed. But again, I don't think it's a problem because FDR can also be calculated fairly quickly. But these are the more serious reasons. Bonferroni is the more strict one of the two. So if a false negative is not that big a problem to you, let's say you have a very large sample size or the effects you're interested in are very large and very consistent, then just use Bonferroni. You're on the safe side of being wrong. If on the other hand, the difference you're studying are small, you're working with a limited sample size, or the effects are not very consistent, then this FDR correction is a lot more attractive because it will give you more significance while still having corrected for multiple testing. There's one important reason you would use Bonferroni over FDR that I haven't written down here, and that is if tests are correlated. So if you're doing tests that are related to the same thing, then FDR correction is not the right way to go about it, and it will artificially inflate the number of significant results. Also, one thing you should be careful with using FDR correction is not to include nonsense tests. We haven't seen nonsense tests yet, but an example is when you do linear regression, you always get all the outputs, right? So you'll see that the intercept has a p-value, the slope has a p-value, the second slope has a p-value, etc. But almost always, this p-value for the intercept doesn't have any meaning for our research. The fact that the line doesn't go through 0 but through 1, for most research this isn't interesting. But because most intercepts don't go through 0, this test is almost always significant. If you would include this and you do FDR correction, then it says, okay, intercept is significant, apparently the penalty should go down. So that's tricky, because now you're using a test that is not interesting to your research to conclude that other tests should be treated less severely, right? So that's the more complicated reason. These are the ones you should know for the exam, but there are reasons you would use Bonferroni, but simply it boils down to, if you're more worried about false positives, Bonferroni. If both false positives and false negatives are important, then false discovery rate correction is better. That's it. That is the concept of multiple testing. Are there any questions about this? Yes? This one?
Yeah, because the FDR was rank divided, k divided by rank.
Yeah.
So why didn't the second and third p-value right?
Yeah, good question. The third one should be equal to this, right? If we go back, we'll see that there is this step that preserves the original order, right? So if you rank, it would be kind of silly if you apply this correction and at the end of the day, this p-value is not significant and this one is, right? Because they're the same. So what FDR correction does is it says, okay, every p-value should be at least as low as the next p-value in terms of rank. And this order preserving step, that causes a lot of the p-values to be the same. Yeah? Might look weird, might intuitively seem that that's wrong because a lot of p-values are now the same, which doesn't necessarily make sense. But an easy way to think about it is just that these values don't really matter. It's whether you're going to reject the null hypothesis that matters. And that is what this correction protects against, that you will not do that too often. Yeah? Any other questions? Okay, if not, then I will show the assignment of the day. And after I do that, I want to show one more thing that I thought was interesting. Okay, so just one thing. There's a chapter on chi-squared here. We will not do that until tomorrow, so you can skip all the way up to multiple testing. This is the lecture I just gave, just in a shorter format. These are the exercises, right? So these are, some of them you have to use the formula for the family-wise error rate. Some of them you have to apply multiple testing correction. And some of them are more about, correct interpretation of values. These are all types of questions you could expect on the exam. We are very strict about multiple testing correction on the exam. This is something you should really understand well. That's why I try to keep the lecture short. There's not too much things on the side that you should also know. Just make sure that you understand this part. This is really the most important part for significance testing. Okay, then the last thing I want to show, there's this question 3. It's about the reproducibility crisis. Has anyone ever heard about this? It's also called the replication crisis. So there's this thing. There was a paper a couple of years ago, maybe 5 or 10 years ago, that says that I don't know the number, but let's say 25% of published science is wrong. Something like that. I'm sure someone has read a headline like that before. This is what they're talking about. There's a big problem where people either don't correct for multiple testing, don't even know what it is, only report the p-values that were significant, which is like not correcting for multiple testing, and a lot of other questionable research practices. In many fields, especially psychology was blamed for doing this, but also biology, chemistry, and even physics. So this is a large problem in all of science, that people don't know what this is and don't realize that using a lot of significance tests in your study and not correcting for it poses a real problem. So why is it called the reproducibility crisis or replication crisis? Because it boils down to it is very hard to replicate other people's research. Most research cannot be replicated, and that is insane if you think about it, because you should be doing research in an objective way. So, you know, most of the results should be the same if someone else does them. That's what you would hope, right? Because we're looking for the truth in science. But unfortunately, that's not quite the case. So again, please study this well. Multiple testing correction is a really important subject. But what's at least as important is that you correctly understand what a p-value is and what a confidence interval is. If you know the interpretation of those, you can just learn them by heart and not really understand them, and then maybe 1 or 2 years later you start to understand. That's also fine. Just make sure you know the correct interpretation by heart, because there are a lot of wrong ways to interpret it, like the chance that the null hypothesis is true, which is not what the p-value means. So we can talk about that tomorrow. If any of these sound to you like they could be correct, even though they're not, then we can talk about that tomorrow. Last thing I want to show before we get to the practical is just that the reproducibility crisis is real. I had to find a way to find bad articles. It turns out it's really easy to do if you just search for p less than 0.05, because of course this returns a lot of articles that rely on this statement a lot. And articles that do that usually are the ones not correcting for multiple testing correction. So I went over these. The first 7 of them, only 1 of them uses multiple testing correction and applies it wrong. The other ones don't apply any form of multiple testing correction. Let me show you one example. Let's just go to the very first one. So just have a brief look at this results section. Look at how many p-values we see. If you were to make any changes in policy, or base your next study proposal on this, then the chance that you're studying something that doesn't make any sense is just ridiculously large. So I just wanted to show you that this is in fact a real thing, and a lot of people don't know this. Easy way to see is just go to the method section, go to statistical analysis. If they do a lot of tests and they don't mention multiple testing correction, you can assume that they didn't do multiple testing correction. And then, as a mental exercise, just count the number of times they use a test, and you can calculate the chance that they have at least 1 error in their paper. And it turns out that the chance is rather large. So, I think it's very disturbing, and I really hope that none of you are going to publish research like this. Okay, are there any other questions? Otherwise, you can go work on the practicals. Oh, I have one more thing to say. Yesterday we were supposed to have 1.4.31, I think, which is on the other end of the hallway. We don't have that room, but we put some tables and chairs in the old data science center. If you exit the hallway and then enter through the door over there, it's over there. Yeah, if you can't find it, I will lead you there. So I saw a lot of people sitting in the lunch area. Fine by me, but if you're like, well, it's too noisy for me, you can sit over there if there's no space here or next to us. Yeah, no more questions? Then that's it for today. and good luck on the assignment.